As you can see, we're going to talk about integration as normal, and we're going to use the method of partial fractions to integrate. Now, let me remind you that many times we find a very useful substitution technique if we can get to the form, the integral of 1 over u du, because we know that that will integrate as the natural log of the absolute value of u plus our constant integration. So if we can do an appropriate substitution so that we get 1 over u and a du, then this is an easy integral to accomplish. Now, here's an example of doing that. Okay, we have the integral of x squared plus 1 divided by x cubed plus 3x minus 4 with respect to x. Now, one thing to try, and something that we've practiced a lot, particularly in Calculus 1, we might try, and we have a hint of maybe this would work, but we might try letting u be x cubed, the denominator, x cubed plus 3x minus 4. And the hint that it might work is when we look at the derivative of u, we get a 3x squared. Now the 3 I'm not so worried about yet, is the x squared, and I have an x squared factor in the numerator of my integrand there, don't I? And so at least it's worth a try. Well, when we actually find du, we actually find the derivative to find du, we would get a 3x squared, derivative of x cubed, plus the derivative of 3x is just 3. And of course, the derivative of minus 4 is 0. So we get a 3x squared plus 3 times a dx. Now the problem is when we look at our integrand is just an x squared plus 1. See, we're trying to match to what we have. We have an x squared plus 1 dx, and would like to be able to replace that, of course, with a du, but we don't have that. But if we pay a little more careful attention to what we have over here on the right side, we have a common factor of 3 there. So if we think about factoring that 3 out, we have 3 times x squared plus 1. Well, we can always change, that's all we're off by is a factor of 3. So here's what we're going to do. We're going to change what we have in the numerator, and we're going to write it as a 3 times x squared plus 1. Okay. Now, since I'm putting a 3 factor inside the integral, I need to offset that with a 1/3 factor on the outside. And of course, we have this dx, and we have an x cubed plus 3x minus 4. Now, the way we've set this up, all of this is a du, isn't it? And this is a u. So this becomes 1/3 times the integral of 1 over u du. And we know very easily then that's 1/3 times the natural log of the absolute value of u plus our constant integration. But specifically this time we have u is x cubed plus 3x minus 4. So we have completed the integral. Now, so the point is if we can get this 1 over u du form, it's pretty easy for us to integrate. Now, we turn our attention, though, to what about? See, what about the case if we have the integral of, say, 2x plus 1 over x squared plus 2x minus 3 with respect to x? Well, if we try that same thing here, if we try to let u be x squared plus 2x minus 3, du would end up being 2x plus 2 dx. And the problem is now we could certainly factor out a 2 again, a 2 this time, but then we're completely different than what we have over there, because on the left, what we're trying to integrate is a 2x plus 1, not a 2 times an x plus 1. So this becomes a problem. But enter partial fraction decomposition. Remember, partial fraction decomposition. If we look at what we're trying to integrate, we take a look at, in this case, what we're trying to integrate. Many times when we decompose a fraction, we end up with linear factors that we could call u. We can turn this into 1 over u forms. So remember how this partial fraction decomposition goes. We first factor the denominator. Well, can we factor the denominator? That ends up being a big issue, doesn't it? Let's see. How about an x plus 3 times x minus 1? That will do it, won't it? Okay. Well, then first we had to notice that it was a proper fraction. Otherwise, we couldn't do this. But it is a proper fraction. So we know when we're done, we know when we're done doing this decomposition, we're going to end up with some constant over x plus 3 plus some constant over x minus 1. Now, the problem is finding the a's and b's, but look what we're doing. We're turning in integrating this with respect to x into integrating these with respect to x. And these can be integrated by making a substitution for u to be x plus 3. So let me note this real quickly. Anytime you have an integral of the form some constant divided by a linear function, okay, let me say in this case some bx plus c, those are lowercase. Anytime we have that, we can factor out the a that's in the numerator, and so it had nothing more than the integral of 1 over bx plus c with respect to x. And if we let u be the denominator, then du is going to be nothing more than b times dx. And so we could always put this in a form, we could always put this in a form as we could say, well, let's put a b, lowercase b, up here. We'll have to offset it by 1 over b in the denominator. And now we have our du and we have our u. So this ends up being a over b. The integral of 1 over u is natural log of u, absolute value u, which is bx plus c in this case, plus our constant of integration, not to be confused with the c in the absolute values. Now, my point here is not for you to remember this little exercise that I just did. My point is for us to recognize that many times when we use partial fraction decomposition, we're going to get multiple fractions that we can easily integrate. So we should consider that as some kind of possibility, something to try. And we'll maybe let's complete this particular problem on the next page. We'll actually start from scratch and complete it on the next page. Okay, we're going to complete the problem, and you see it there. So remember, the first thing we really ended up doing, let's kind of keep track of what we were doing, is that we went ahead. Well, let's just rewrite it. Okay, now what we decided to do, and it's worth this in many cases when we have a rational function we're integrating, and it's a proper rational function, we try decomposing it. So we take that fraction and we factor the denominator. I forgot how I factored it, but let's say x minus 1 times x plus 3. I think I had those reversed, but that's all right. Okay, and so we know the form is going to be a over x minus 1 plus b over x plus 3. So sometimes I'm asked, well, does it matter which order we have those factors in if we factored in a different order? Well, in one case you may say a is over x minus 1. In another case you may say b is over x minus 1. But regardless of which you do, when you solve for a and b, you'll get the proper numerators, whether it's called a or whether it's called b. Now, when we go through this, remember we get a 2x plus 1 And on the right side, we'd have an x plus 3 times an a, and then we'd have an x minus 1 times a b. And when we go through the process, one thing we could do is let x be equal to 1 and solve for a, or we could let x be equal to negative 3 and solve for b. But under any circumstance, I'm going to assume that you've looked at the partial fraction decomposition and we know how to decompose this. And if we do, then we'll get an a value of 3/4 and a b value of 5/4. Okay, that's assuming we know how to do this decomposition. So here's what we've got then. Rather than integrating this one single fraction, we're going to decompose it. And when we decompose it, we have a fraction that has a 3/4 over an x minus 1, plus a fraction that has a b, which is 5/4 over an x plus 3. So all we've done is decompose that fraction. Well, what that boils down to then is we have two integrals to worry about. We'll just integrate them separately. So we end up with an integral of 3/4 over x minus 1 with respect to x, plus the integral of 5/4 over x plus 3 with respect to x. Well, in that first integral, we can factor out 3/4. So we have 3/4 times the integral of 1 over x minus 1 with respect to x. In the second integral, we can factor out the 5/4. So we have 5/4 times the integral of 1 over x plus 3 with respect to x. Now, in the future, I may go through this kind of rapidly, but I'm going to make sure that we put in all of the, if you will, ugly steps. In this very first fraction, integral, I'm going to let u be x minus 1. I'm going to do a substitution. And if I do, then du is just going to be 1 times d. The derivative of x minus 1 is just 1, isn't it? So du is dx. Oh, well, that makes that real easy then, because the integral of 1 over x minus 1 with respect to x is a complete easy conversion. That's the integral of 1 over u du. And so that's the natural log of the absolute value of u, plus a constant, okay, we'll deal with in a second. So this integral, I guess I got ahead of myself, okay. We're looking at that single integral, and we can do the same thing here, but let's kind of wait for it just a moment. So this would end up being 3/4 times the natural log of absolute value of u, but u is x minus 1, plus 5/4. Well, what we're going to have here, see, we're going to do the same thing. If we let u be x plus 3, then du is nothing more than dx. And so what we have in this case, once again, is just the integral of 1 over u du. Okay, well, the integral of 1 over u du is the natural log of the absolute value of u, but in this case, u is x plus 3. And the only thing we don't want to do is forget the constant of integration at the very end. So applying partial fraction decomposition to our integrand, that is what we're integrating, made this a fairly simple problem. I just got a little headline here. The denominator of our integrand contains repeated linear factors, but up here the denominator included only distinct linear factors, is what we might say. None of them are repeated. Distinct linear factors, that's the denominator. Well, and if you looked at the video that is about partial fraction decomposition, didn't include any integration, we actually saw this particular integrand dealt with. So what we normally do, the way we would approach this is we would start by factoring the denominator. I mean, we might do that kind of offline here. Okay, let me just rewrite the whole problem. Oops, that's 2x cubed plus 4x squared plus 2x, and we're integrating with respect to x. Now, if we go to the side and we integrate, if we factor that denominator, here's what we're going to get. We're going to get you see that it has a factor of 2x that's common all the way through, and then that'll leave behind x squared plus 2x plus 1, and that will factor as x plus 1, the quantity squared. So I'm assuming that you can do that. I'm not worried about showing you those details. Now, like I said, in the video that was on partial fraction decomposition only, not dealing with the integration part, what we found out, see, when we did this, we found out that this would look like 4x squared minus 1 over 2x times x plus 1 squared. The decomposition would be a over 2x plus b over x plus 1 to the first power, and then plus some c times x plus 1 over x plus 1 to the second power. Okay, well, if we do, and then what we ended up finding out is in the decomposition, we solve for the a, b, and c, and we got a is -1. So we have -1 over 2x. And we found out b was 5 halves. Okay, so 5 over 2, 5 halves over x plus 1, or b. And then we found out c was actually -3 over 2. So we have -3 over 2 over x plus 1 squared. So what that means is we can come in here, and I'm cramming this stuff in again, my apologies. We end up with the integral of -1 over 2x plus 5 over 2 divided by x plus 1 plus -3 over 2 divided by x plus 1 squared. And we're integrating with respect to x. So that actually gives us 3 different integrals, doesn't it? So we will say, okay, well, look, this is the integral of -1 over 2x with respect to x, plus the integral of 5 over 2 over x plus 1 with respect to x, plus the integral of -3 over 2 divided by x plus 1 squared with respect to x. Now, let me turn pages, and I'll actually rewrite this on the next page, and we'll go through the steps here. I'm not going to always go through every single step. I'm giving you the idea of what needs to be done, but we need to notice how I would approach this at least. Okay, I want to clean up what we're working on before I go much further. In this very first integral, and sometimes we don't think of doing this, but in this very first integral, notice that integrand, -1 over 2x, is exactly the same thing as a -1/2 times a 1 over x. And so I could factor out a -1/2, and I'd have the integral of 1 over x dx. And notice in this second integral, that constant of 5 over 2 in the numerator, I can think of that as 5 over 2 times the fraction 1 over x plus 1. So I'm going to factor out the 5 over 2, and I'll just have the integral of 1 over x plus 1 with respect to x. And then, and then in this particular integral, okay, sorry about that, I'm going to factor out a -3/2. So I'll say minus 3 over 2 times the integral of 1 over x plus 1 to the power 2 with respect to x. Now, I hope without much fanfare, in this very first case, we recognize the integral of 1 over x with respect to x is the natural log of absolute value of x. And in the second integral, we have 5 halves, and we can do a u substitution, make u x plus 1, and things will work out. We just went through a couple of cases like that, situations like that. So in the second integral, we'll get the natural log of the absolute value of x plus 1. Now, I've held this one off because it may not be quite as obvious yet, okay? And that's the idea. The more you work on these, any of these integrals, things become more obvious. Now, what I'm going to do here, okay, what I'm going to do here is I'm going to do a u substitution. I'm going to let u be x plus 1. So what does that mean? I have the integral of 1 over u squared, of course, dx. Well, that's not a bad problem if I can get a du. Well, when we look here, du, of course, is 1 times dx, or just dx. So this is really the integral of 1 over u squared du. And of course, the integral of 1 over u squared is the same as integral of u to the negative 2, isn't it? And when we integrate u to the negative 2, we get what? Well, we'd increase the exponent by 1, wouldn't we? Okay, and when we increase the exponent by 1, we get a negative 1 exponent. So we'd have u to the negative 1, but we have to have a reciprocal of the new exponent, which is just negative 1. Or we end up getting the negative of u, which is x plus 1, to the power negative 1, or negative 1 over x plus 1. Now, I really believe that ought to be pretty transparent to you, pretty easily done for us. So I'm going to leave it at that. Now, let's go back up to finish this problem. We now have negative 1/2 times the natural log of absolute value of x, plus 5/2 times the natural log of absolute value of x plus 1, and we have a minus 3/2 times a negative, okay, a minus 3/2 times the integral, which was a negative 1 over x plus 1. And of course, let's not forget our constant of integration. So when the dust settles here, okay, that very last term we can make look a little bit better. I'm rewriting everything until I get to that last term. And of course, we have a negative times a negative, which is plus, and 3 times 1 for the numerator, and 2 times the denominator of x plus 1. And so this would be the integral of 4x squared minus 1, all divided by 2x cubed plus 4x squared plus 2x, our original integral. We have done that, and we accomplished it by decomposing the original fraction. Well, so far, again, this partial fraction decomposition is just another tool you put in your toolbox. Whenever we're integrating a proper fraction, that is, a proper rational expression, then this is a tool that we can try. And maybe it's not always the easiest, maybe it's not always the best, but it's certainly something that we can try if we're needing to integrate. And so far, the examples we've looked at have been fairly routine in terms of the integrals that we're left to deal with. And so what I want to do is give you some examples where it goes along in a routine way, but we're also going to run into some issues occasionally that we have to use additional techniques of integration as we proceed. So in this next example, we actually have a denominator that has distinct quadratic factor, irreducible